Hi. So we looked at autoencoders, we looked at the data manifold, the latent space. We then looked at the contrastive learning, also known as metric learning, and we found that metric learning has this problem with negatives, right? So there are just too many negatives. So now let's see. So we're not going to spend too much time on this, but I want us to understand how to do that negative mining, how to find those hard negatives, and also talk about this thing called as the triplet loss. So what is the limitation of pairwise comparison? It only looks at pairs. So it's just a binary decision. Is it the same or different? And it has this, notion of ranking missing, right? Because you're not ranking between, let's say, three. You're just saying same or not. So the idea, the question that people asked were, can we kind of do a ranking? Can we have like one, which we may call the anchor, and then can we look at like a positive and negative simultaneously in relationship to that anchor? So can we compare the anchor to a positive and negative? So what we mean by that is, let's say we have an anchor, right? And now instead of this one network, we have three networks. Okay, the three networks then give us these latent spaces, and our latent spaces for let's let it be the same as earlier, which is two-dimensional. And now we give it three, let's say, data points, in this case images, right? And one is an anchor, let's say it's a 6, and we then want to say that, okay, what is, and then one negative and a positive, right? So my anchor is 6, my negative is, let's say, 9, and then my positive is another 6. Yeah. And then look at the question we are asking, right? We are saying that before learning, maybe the distance between this two, let's say between 6 and 9 is, let's say, 0.4, so it's low. And then between 6 and 6, let's say it's 0.8, right? All we are saying is that the distance between, so whatever is the distance between me and the negative, I want the distance between me and my positive to be less than that, right? So eventually, after training, what must happen is it should get lesser, right? So before training, let's say our distances were, let's say, for the anchor, let's say the distance to the positive was more than that of the negative. So this is, let's say, d positive, and let's say this is d negative. So in this case here, our d positive was greater than d negative, and this is not what we want. But after the machine learning happens, after the machine learns, we want the d, so this will flip, then d positive now becomes less than d negative, and we are happy with that, right? So anchor is your reference image, positive is of the same class, and negative is of a different class. So now, if you want to write it mathematically, it's just this actually. But when you write it in math, when you want to condense it into that one equation, it just looks difficult. So it's essentially like your ReLU. It's a max function. And what is this max function with? This is the distance of the anchor to the positive, right? So this is my d positive. This is my d negative. And all it's saying is my d positive should be greater than d negative with this alpha margin. This is again a margin. Essentially, it says this: my d positive plus alpha should be less than d negative, meaning my distance to the positive should be less than the distance to the negative with this kind of a margin, with this kind of a buffer. And you can then write it as a max, because if this is already the case, if my d positive plus alpha is already less than d negative, then my loss is 0. Yeah? And if it's not, then you actually minimize this loss. Then what do? You say d positive minus d negative plus alpha. This becomes my loss, and this is the value, right? This is a scalar. It belongs to just a real number, and this is the scalar that we then try to minimize. So that's all that there is in triplet loss. It's very similar to the metric loss, the contrastive loss, but here we have added now this notion of an anchor, and because of this we have ranking, right? We are saying, okay, for me you have to be close and you have to be far, but not in a absolute sense, in a relative sense. All I want is to kind of look at, my positives and my negatives relatively. Yeah. So there is no, let's say, very concrete positive, like say yes or no, right? It's kind of relative based on the distance of the anchor to the positive and to the negative. And alpha is my safety margin, right? And typically it's in the range of, let's say, 0.2 to 0.1. The distance to the positive should always be less, the distance to the negative should always be high. And we have discussed this earlier. So what is a hard negative, right? So what is an easy negative? Easy negative is, let's say, distinguishing a dog with a table. And here we very quickly learn it, and this is why the gradient becomes 0. But what is hard? Hard is where our negative is, let's say, similar, right? And that is where the learning is actually meaningful, because those are the ones where we are probably making mistakes, right? So we need hard negatives, and we show a network of wolf. When the anchor is a dog, the network will initially think it's a dog, and when we force it to push it away, it looks at the ear, snout, and eye spacing, and eventually learns that it's a wolf. And there are two ways to mine these hard negatives, right? To mine those wolves. So for this dog, I still have to kind of, for my negative, I need to take them from a different class, right? But I don't want to take them from the class table, right? I need to find a class and an example in that class that is hard. So I will take it from the wolf class. And there are two ways to do this negative mining. One is the offline mining, and the other is the online mining. So the offline mining is like very simple. What you do is, you trained a little bit, let's say, you trained one epoch, and then you stop. You take the model, and then you kind of run it on one positive, right? You run it on something. And then you list, the scores for this to end. So what you usually do in practice is you create this matrix, right? So you have, let's say, your let's, instead of positive, now let's call it, so let's first make this matrix. And in this matrix, what we have are these data point 1, and then we write data point 1, data point 2, data point 3, data point 4, and so on. Yeah. Okay. And here we have the same thing. So it's a data point 2, data point 3, data point 4, and so on. And we find the distance, right? So here they're all the same, and we find the distance between D1 and D2, and we write something. We find the distance between D1 and D3, we write something. It will be a symmetric matrix, right? Because the distance between D1 and D2 will be the same as the distance between D2 and D1. Similarly, so the D2 D1 distance will also be 0.6. And the distance between D3 and D1, so D3 and D1 will also be 0.7, and so on. And now we will know from our data set, okay, D1 and D3 are actually positives, but D1 and D2 are negatives. And then we can do a lookup in this matrix that we have created, in this matrix over the entire data set, and then we can choose to mine our negatives based on whichever are the hardest, wherever the distance is the maximum, and so on. But this is a very tedious and time-consuming task. You've stopped your training, you're running over the entire data set, you have a gazillion of these negatives, right? So it becomes really hard to do this. So instead, what you want to do is you want to do it online. You want to do it only at the batch level. And what I mean to say by that is, I'll show you in the next slide. Just remember that FaceNet, the Face ID paper, the one where Google kind of created this FaceNet, they do it on large batches of size 1800. So they have 1800 images of faces coming in, and then within that batch, they do this negative mining. How do they do it? Let's say you can do it for faces, you can do it even for patches, image patches. But for simplicity, let's just say this is face 1 anchor, and this is again face 1 positive, and then this is face 2, and these are all different images of phase 3 and phase 3, right? Slightly different, phase 4 and phase 4. And then for these images of faces, you also create their embedding. So A1 is the embedding or the descriptor, and so on. A2 is the descriptor for the first one, right? So for F1 it's this one, and so on, right? So F2 like this. Yeah. And Then we create this, 4 cross 4 matrix, this one, like we were creating over the entire data set. And we compute the distance. So we compute the distance between, so now we know that our A1 and P1 are positive, right? Because it's the same phase. So A1, P1 is positive. Similarly, A2, P2 is positive, and then everything else is negative. So we know, so we have already been given the positive and the anchor, right? So we call this, the first one the anchor, the second one the positive. But then which negative should I use for this triplet, right? Because we want to do the triplet loss. So it is very simple. What you want to do is you want to look at this row and you want to look at the, you want to look at this column and you want to look at this row. So this column and this row. So this one is not interesting because this is just for the positive. But then between these three, you find the minimum, you find the distance which is the maximum. So we found that, okay, this is giving me the maximum distance. Yeah. And then similarly, we find that in this column, this one is giving me the maximum distance, right? So so we got through this row, we got this one. For the column, we got this one. And then between these two, we compare, right? Between these two, we compare which one is still harder. And then we found out that, okay, A2 is harder. And so we then took A2. So then my triplet becomes obviously this which is already there, this which is already there, and this A2, right? So the A2 is then maybe this one, right? So you then becomes, the F1 anchor, F1 positive, and then this another F2 positive. So from that batch, I found which is the most difficult for my current triplet, and then I form a triplet based on that. In practice, you have many positives, right? You have an anchor and then many positives. And then you also have all these different rows with different classes and many positives. And then you try to kind of form many positive pairs, many negative pairs, and then do that cumulatively before updating the weights. And so this is how you do negative mining within a batch. And that's all that there is. So FaceNet, the one for Face ID from Google, it's a Inception net, and we'll talk about Inception net when we talk about the history in next week, in week 5. It uses a batch size of 1800, we spoke about it, and it does this hard negative mining within the batch. Training is on 200 million face images, 8 million identities, and with aggressive augmentation, data augmentation. So we'll also talk about data augmentation in the next video where we talk about SimCLR. The architecture is simple, it's like this batch of positives of different subjects, and then you have like your, deep architecture, your model. And one interesting thing they do is they do this normalization. They do this L2 normalization, which is differentiable, by the way. So you can think of the function which does L2 as activation layer, because then the distances become meaningful, right? Because then you can actually do the cosine of them, because then it's a normalized vector. And finally, you compute the triplet loss after doing that in batch negative mining. And finally they found that this 128 dimensional embedding achieves this superhuman face recognition performance. They also did a comparison with your normal contrastive learning. So the blue one is your normal contrastive learning, and they see that most of these pairs become saturated very, very quickly. So during early training, 80% of these triplets are active, but then late training, only 5% of these triplets are active. So learning slows down dramatically. And when you do contrastive, it kind of saturates very early, because now the learning is very, very weak because you don't have that much of gradients coming in. But when you do triplet, it works much better and your loss decreases and it kind of converges.